Hello, welcome to my video on data structures. This is part 2 for the linked list data structure. In this video, we will introduce fundamental operations for the linked list. We will talk about 3 types of operations: data access, data insertion, and data deletion. Note that we will allow for the insertion and deletion at arbitrary locations of the linked list. Meanwhile, we will allow the insertion and deletion of a linked list segment in addition to a single data element. In some cases, the insertion of a linked list segment is also called a splicing operation. Let's begin with the representation and structure of the data elements stored in the linked list. As we have introduced in the last video, each data element in the linked list contains 3 fields: the actual data content, the pointer to its previous neighbor, and the pointer to its next neighbor. In the figure here, we use data to represent the actual data content. It could be, for example, the price and quantity of an item you sell in your store. We also have 2 arrows, namely prev and next, and they are the pointers to the previous and the next neighbors. We call the entire block that contains all 3 fields a node, and we say that we have a list of nodes in the linked list. In each linked list, we have 2 special nodes, the head and the tail. As the name suggests, the head is the very first node and the tail is the very last node in the linked list. The data fields of the head and tail store nothing. In other words, no actual data content is stored in the head nor the tail. Also, the prev pointer of the head node and the next pointer of the tail node are both null pointers, which means that they point to nowhere in the memory space. The reason for including the head and the tail is to make it easier to consider boundary insertion and deletion cases. For example, the boundary case can be inserting the first element into an empty linked list or deleting the last element from a linked list. With the head and the tail nodes, we can always assume that there exists node before and after the node being inserted or deleted. The figure shows an empty linked list with nothing between the head and tail. We will always keep track of the addresses of the head and tail, and we use the blue color to indicate that their addresses are known. Here we show a linked list with only 1 data element. We can see that the actual data element is placed between the head and the tail nodes. Now, let's look at the data access operations. The linked list data structure supports 2 types of data access operations. We can either search the entire linked list for a specific data element, and we can retrieve the information of a data element given its address. For search, we simply start with the head node and check the data elements one by one. Such an operation will take linear time. The second type of data access operation is trivial. It is often used together with the search operation. For example, if we want to reduce the price of an item from $10 to $7, we can first search for 10, obtain the address for the item, and use the address to access the data and update the price. Let's look at data insertion. For insertion, we are given the address of the location we want to insert. For example, if we want to insert a new data element between data element i-1 and I, we will know the address of data element I. Let the address be pi, and we use the blue arrow to indicate the information is known. Now, let's say that we are inserting data element x between data element i-1 and I. We will first request a memory space to hold data x. In other words, we will create a node for data x. Once the node is created, its address is also known to us. Let's call it px and color the corresponding arrow blue. To insert data x, we need to modify 4 links. The first link we need to modify is to assign the prev pointer of data x to data i-1. The second link we need to modify is to assign the next pointer of data x to data I. We have labeled the links added in the 2 steps with 1 and 2 in the figure respectively. And we can implement the changes with the 2 lines of code shown here. The third step is to make the next link of data element I-1 point to data x. And the fourth step is to make the prev link of data element I point to data x. The changes of the link are labeled 3 and 4 in the figure respectively, and they can be implemented with the code shown here. In the marginary case, we are trying to insert a segment of linked list that begins with the data element x and ends with the data element y. The insertion also contains 4 link changes and can be easily inferred from the single data element insertion case. In step 1, we make the prev link of data element x point to data I-1. In step 2, we make the next link of data element y point to data I. In step 3, we make the next link of data element I-1 point to data x. And in step 4, we make the prev link of data element I point to data y. Okay, let's take a look at data deletion. We are trying to delete data element I from the linked list. As a result, we will know the address of the data element that needs to be deleted and let it be pi. Data deletion is relatively easier compared to data insertion, and we only need to modify 2 links. First, we make the next link of data element I-1 point to data element I+1. Second, we make the prev link of data element I+1 point to data element I-1. The changes implicitly skip data element I, therefore deleting it from the linked list. And we can see the implementation as the 2 lines of code shown here. Similar to data insertion, we may delete a segment of the linked list. Say we are trying to delete the segment that begins with data element I and ends with data element j. The link changes are also similar to the single element deletion case, and there are 2 steps. First, we make the next link of data element I-1 point to data element j+1. Second, we make the prev link of data element j+1 point to data element I-1. In summary, we have discussed the fundamental linked list operation in this video. We have talked about data access, data insertion, and data deletion. We can see that data insertion and deletion can both be implemented with several pointer changes. In this case, each insertion or deletion can be done in constant time. This is the major advantage of the linked list data structure. In the next video, we will continue our discussion with more implementation details. Thanks for watching and hope to see you next time.